All right, great. Thanks everybody for being here. I'm excited to have a chance to join you all for the next few days. Okay, so I've come a pretty long way, and but I'd like to make use of all of that flight time by talking with all of you. So we'll have a few days together. There'll be meals and whatever breaks, and I just want to encourage everybody just to break into whatever conversation I'm having and come and say hello and chat. Sometimes it takes a little encouragement to kind of cross the boundaries and talk, but I'm totally here for that purpose. All right, so I chose a set of topics that have to do with quantum simulation. So quantum simulation, you might regard as sort of the use of, in this case, cold atom quantum systems to simulate the physics that occurs, for example, in condensed matter systems. But I'm here to kind of burst that bubble a little bit, because that's not really what condensed matter physics is like. In fact, in condensed matter physics, we don't even know what is going on inside of material. So as I learned from teaching solid state physics a number of years ago, solid state physics is a whole slew of approximate treatments to a problem that is much more complicated than we even know how to describe. And in fact, something as simple as a chunk of sodium metal is not something we can quantitatively match to theory. We have qualitative theories for what happens in this kind of a simple metal, but no one is going to attempt to make a precision measurement on a piece of aluminum and match it to the precision outcome of a condensed matter theory model, because these things don't match each other, right? What happens in real condensed matter systems is immensely complicated. And now that is part of what makes condensed matter physics so wonderful, which makes it so rife with discoveries, because there's sort of more things that can happen in condensed matter physics than we can predict, because it's a little bit of an intractably complicated problem. So what is quantum simulation? Quantum simulation is sort of realizing that we've fallen in love with these sort of models of condensed matter physics, which we think give kind of a simplified representation of at least some of the phenomenology that happens inside of a many-body real condensed system. But now with the cold atom systems, we can actually make a physical system which is truly represented by an ab initio theory. So if you will, it's like taking condensed matter theory and making experiments out of it. That's, of course, well, not of course, but that turns out to be what drew me to this field. I came into physics intending to be a condensed matter theorist, and then I found, oh, there are these experimental systems that are basically just the same thing. So I get to do experiment, but on topics that are entirely theoretical. And there's a lot of examples through the sort of history of cold atoms as a many-body quantum system that is understandable. Examples, some of which I've been more involved with and others less involved with, but many sort of hallmark developments in our field. And in today's talk, I'll talk some about applications to understand of cold atom systems, to understand band structure and periodic systems somewhat better, and I'll emphasize this connection between geometry and physical properties. I'm giving a talk also on Monday, and I will at the Raman Research Institute, and I'll focus instead more on sort of the mesoscopic physics work within my group. Okay, so I'd like to sort of cover two large topics in the presentation today. One is the study of geometric effects in band structure. And the second one is our first attempt to start cooling a new set of atoms that have not been brought to the ultra-cold regime before. I'll connect it through in some way back to the topic of topology. All right, so we'll get going with the first topic. So, okay, so now I'm gonna almost backtrack to what I said. When we try to understand condensed matter physics, usually the starting point is band structure, right? The states of itinerant particles in a periodic potential. And band structure has a lot of important features. One of them, of course, is that there's bands and there's gaps. So that explains, differences between metals and insulators, and the density of states tells us about the superconducting transition temperature. But there's other aspects of band structure that also kind of rise to the fore, in particular, in the few very, very clean experimental systems, condensed matter systems, where there is a strong connection to band theory. And so examples are, let's say, in something like graphene, we know that there's very special properties of graphene that have to do with the fact that there's a touching between two bands at a degenerate point, and the variation of not just the energy, but also the states themselves near that touching point tells us a lot about the physics of graphene. There's also systems where there's quadratic band touchings. For example, in bilayer graphene, this occurs. And the fact that the energy rises quadratically and not linearly away from this degeneracy point has some very strong implications on the material. And then finally, there's a lot of interesting physics that happens if we turn band structure into flat bands, which you can do, it turns out, by placing one sheet of graphene over another and twisting by a small amount. And in these flat bands, you get rather interesting states of matter. So if we want to understand the connection between band structure and material properties illustrated on this slide, we should create a system that has band structure and study it. And in my lab, we've been following the lead of many other groups already, using optical lattices as the periodic structure. So inside of a vacuum chamber, we intersect laser beams that come in our case, from 3 separate directions, all lying in a plane. And at the intersection of these laser beams, there's a periodic pattern of intensity. Atoms move within that periodic intensity and behave like electrons in a crystal. In our particular crystal, we use 2 different colors of light that have an exact 2-to-1 wavelength ratio. And I'll show you in a second, overlaying them allows us to make interesting lattice configurations. And another really important aspect of our system is we have an ability to change the phases, or if you will, the frequencies of the different beams that are intersecting in a very controlled manner using some closed loop feedback. And that allows us, it turns out, to take the lattice and move it around spatially, even rapidly, along any trajectory that we want. And that'll be relevant to how we probe aspects of band structure. So what kind of lattices do we gain access to? So if we just look at the green light, so the light at 532 nanometer wavelength that intersects, it creates a triangular pattern of zeros of intensity. And it turns out that both rubidium and potassium atoms, which we've been working with in our experiments, are attracted to the 0 intensity spots in this lattice. They fall into a triangular lattice geometry. The intersection of the longer wavelength beams creates the same intensity pattern, but now because of where the wavelength lies with respect to the resonance frequency of our atoms, the atoms are attracted to the high intensity spots of these laser beams, and they fall into the site of a honeycomb lattice, like what I just showed you about graphene. So that's kind of a good analogy for us. And then by overlaying these 2 colors in a very particular relative manner, we can also make this interesting lattice configuration known as the Kagome lattice, which I'll mention just at the very end. But most of the results I'll tell you about for the next few slides all have to do just with the honeycomb lattice, where we already see some very interesting features. In particular, oh, no, here it is. Already in the honeycomb lattice, we already see linear band touching points, the Dirac points, which we know from graphene. There's quadratic band touching points among the upper levels. I won't talk about them for lack of time, but we've looked at them. And there's also some bands that become flat in the limit of a very deep lattice. So it kind of has all the aspects of band structure that I find really compelling. All right, so let's say we want to study in particular the physics of these band touching points. All right, so we need to have atoms in these at the location of these band touching points where the physics then becomes relevant. So we have 2 choices. One is to take a gas of fermions, to fill the fermions to where the Fermi level, like in a sheet of graphene, lies near this touching point. Okay, that's not what we did for the next experiment. Instead, we were working with bosons. Turned out we were working with rubidium atoms. These are bosons. When you get them very cold, they bose-condense in the lowest energy single particle state, which is in the lowest band, and it's down here at the gamma point. And at this point in band structure, there's nothing interesting. It's a very, very boring block state. So we'd like to somehow get the atoms up to these higher points. And the way we do so is by moving the lattice around. So what we do is we first add atoms to a lattice that is stationary. And as I said before, the atoms bose-condense, these bosons, bose-condense in the lowest band at the gamma point. But then we start accelerating the lattice. And from the viewpoint of the lattice, it feels like we've accelerated the atom. So it's kind of the equivalent of putting a force on our atoms. And as a function of the trajectory of that force, the atoms now move from 0 quasi-momentum to somewhere else. And in doing so, we can move them to the location of this linear band touching point and study the features of the states around that band touching point. So at the linear band touching point in a honeycomb lattice, like in graphene, there's a really interesting consequence, not just that the energy rises linearly, either in the upper band or I guess drops linearly in the lower band as you move in quasi-momentum away from the location of that touching point. But also it turns out that there's a very special property of the states right near that touching point. And we can parameterize this by writing the states. So the states, if you remember, have a unit cell wave function on top of a running wave component. And that unit cell wave function can be written as a superposition of the particle being either at site A or B. That's a two-level system, which we can represent as a pseudo spin 1/2. And in the language of that pseudo spin 1/2, the states near the Dirac point, so if I move in quasi-momentum away from this linear band touching point, the states are like those of a particle in a transverse magnetic field, where the orientation of that magnetic field has to do with where you are in quasi-momentum away from the Dirac point, and the magnitude of that magnetic field rises linearly as you move away from the Dirac point. And drawing this magnetic field orientation already implies for you what are the two states in the upper band and the lower band as a function of quasi-momentum. And you already see from this kind of diagram that there's a kind of a singular thing that happens right at the Dirac point. So the states in the upper band and lower band are fully defined everywhere, but at the linear band touching point, you don't know quite how to define them. But even more so, as you depart ever so slightly from that Dirac point, the state of the system can be dramatically different depending on the direction in which you've left the Dirac point. So this geometric singularity in the band structure has been interesting for cold atom experiments to probe. And there's a couple of ways to do it that have been realized in the literature. One is to measure Berry phases. So it turns out, if you took a particle in a magnetic field and you dragged it around so where the magnetic field winds around a loop and the particle was lying on the equator, you would pick up a Berry phase of pi. So you can measure that by dragging something around the loop. And that's in fact how this was done experimentally by the group in Munich. So they took a gas of atoms against a Bose condensed gas. They prepared it at some place in quasi-momentum, and then they split the gas into two separate spin states. Then using spin-dependent forces, they dragged these atoms so that they encircled the Dirac point. And then they finished up the interferometer by again driving a spin transition. And they found that every time the path that they dragged the atoms circumscribed the Dirac point, their interferometer picked up an extra phase of pi. So that was cool. It kind of shows that there's a Berry flux that's concentrated right there at the Dirac point, and the Berry flux altogether integrates up to a phase shift of pi. In our experiments, we've looked at a different feature of this singularity, which is also how it affects parallel transport. This was a parallel transport experiment. But we're transporting along a different path, and the path that we're choosing to transport along does not avoid the geometric singularity, rather it probes it directly. And so we take atoms in one of the bands, in this case the lower band, and by accelerating the lattice properly, we move them in quasi-momentum so that they go right into the Dirac point on a straight line, and then on a trajectory that is still continuous but whose tangent is discontinuous, we leave the Dirac point at some turning angle theta. And after leaving the Dirac point, what we find is that the atoms have now transitioned from the lower band to a superposition of the lower and the upper band, where the population in the two bands goes like cosine squared or sine squared of theta over 2. And it's not a super surprising thing to realize once I've told you about this magnetic field representation of the states near the Dirac point, right? Because we initially have atoms that are, let's say, spin polarized down. We move them toward the Dirac point. They're still spin polarized down because the pseudo-magnetic field never changed orientation. But then we suddenly project them onto states which are those of a magnetic field that points, in this case, sideways. And so it wouldn't surprise you that in that case, we suddenly have atoms half in the quote unquote spin up and the other ones in the spin down state. So you get to actually run this experiment in a real live setup. And we do so by, again, taking a Bose condensate that is produced here at the gamma point, pushing them to the Dirac point, leaving the Dirac point at some angle. And then we do this thing called band mapping. I won't go through the details of it, but in the end, we end up seeing atoms in different momentum populations, and those populations correspond to how many atoms are in each of the bands of the lattice. And without explaining these data too much, we can characterize how many atoms, let's say, remain in the ground band as a function of that turning angle. And you see that indeed varies as cosine squared theta over 2, which is a confirmation of the fact that there's one winding of this pseudomagnetic field around the Dirac point. In separate experiments, we also looked at that quadratic band touching point, which also exists in the honeycomb band structure. And there we found that the winding number was 2. So we could see, in fact, evidence that its effective magnetic field winds around twice as you go around that band touching. All right, so getting back to this topic, you'll notice I use the word geometry repeatedly to talk about band structure. And I did so, if you think back, and I've said a few different things. I've told you what is the variation of the lower band states in the region near the Dirac point. That's a certain sense in which I describe geometry. Geometry being like how a surface, I don't know, the tangents to a surface or whatever vary as a function of position on that surface. I've also told you what is the variation of the upper band states. I mean, I told you what that construction was. And moreover, I also told you that the lower band states and the upper band states are pretty closely related to one another. And that, in fact, by manipulating the system, we can undergo a trajectory that flips us from the lower band to the upper band. So the notion of geometry is applied quite a bit to band structure. In band structure, you get bands, which are manifolds of states, and you can describe the variation of the states along this manifold using geometric quantities, just like you measure, you characterize, curved Riemannian surfaces. And there's a number of geometric measures that people use to understand a band structure. The one I'd like to focus on is this thing called the Berry connection, which is a matrix. And here's an expression for the Berry connection. So it's the gradient with respect to quasi-momentum on one of the manifolds, projected into perhaps a different manifold of states. You're probably quite familiar with the diagonal Berry connection, which leads to Berry phases. This happens sort of a characterization of the geometry of a single band, and it has many implications to condensed matter physics. There's also an off-diagonal Berry connection where I ask, how does the variation with quasi-momentum of states on one band project onto states of a different band? That is, if you will, a measure of the relative geometry of two surfaces. All right, so what about these geometric features? Now I'll take a big step back to a kind of a bird's eye view of condensed matter physics and state the following. That condensed matter physics at its start was concerned with band structure, but largely by the presence of bands and band gaps. But then maybe around the 80s or 90s or something, a new understanding started infusing into condensed matter physics that we should pay attention much more to the geometry and the topology of bands, that these also have implications to the properties of materials. Okay, so I've listed a number of examples of how material properties have been connected to topological or geometric properties of band structure. And what I'm going to tell you about in the next few slides is another one of these connections, where we explore the relation between the relative geometry of two bands, which is to say the off-diagonal Berry connection, and the optical response of materials. Okay. So how do things respond when you illuminate them with light? I'm an atomic physicist, so I understand this most when I think about atoms. So when we want to understand how an atom responds to excitation with light, and we can understand any of its responses this way, how much light it scatters, how much light it absorbs, what it disperses, and all that comes in the end from characterizing dipole matrix elements on the atom. Let's say if we're just looking at the dipole allowed transition. That's the quantity that regulates the optical response of an atom. So if an atom has, let's say, an s orbital and a p orbital, we can take this expression here, evaluate it. That'll tell us what is the oscillator strength for driving a transition between these s states and p states. Or it tells us something else too. For example, if an atom is in a superposition of these two states, then now I can basically tell you how the atom is polarized, whether the electric charge is displaced from the nucleus. Okay, so that's kind of how I understand polarization and optical response in atoms. How about for solids? So when you drive a solid with light, stop and think about it, the wavelength of light is typically very, very large compared to the unit cell in the solid. So when we think about optical drive, we're basically thinking about a transition that does not add any quasi-momentum to the electrons. And instead, it drives transitions from one band to the other at the same quasi-momentum. So maybe I should apply exactly the same thought process that I did with atoms. I have to just draw for you what is the unit cell wave function in one of the bands, and in the other bands, I can take their dot product somehow with a position operator inside, and that'll tell me the strength of the optical response to drive this transition. Or equivalently, if I have an atom that's in a superposition of these two bands, maybe I can just draw the electron wave function and realize that for this particular superposition, there's a positive polarization to that direction. I'm so confused. That there's this charge imbalance in the unit cell. But in solid, things are confusing because who's to tell me where the unit cell actually lies? So maybe this superposition of states has a polarization where there's more charge to the right, but maybe that's not true, because maybe if I instead draw this as the unit cell from 0 to A, then now I actually have a polarization to the left. So that's very confusing. And in fact, the theory of optical polarization in solids was in a very confused state of affairs up until maybe the 90s or the 2000s, when people made a kind of cool realization that the optical response and polarization in materials is given by geometric quantities. And in fact, what you should be evaluating in determining the optical response in a material, this off-diagonal matrix element of the position operator, is nothing other than the off-diagonal Berry connection. The relative geometry of two bands. Those things are identical. Or stated differently, if I'm driving my system with some polarization of light and I want to see, let's say, the strength of the response, the rate at which electrons are excited from the lower band to the upper band, what I have to do is take the dot product of that electric polarization vector with this quantity, this off-diagonal Berry connection, square it, and that gives me the matrix element, or the oscillator strength. Okay, so that's kind of weird. I certainly didn't know this going into it. Turns out a lot of people I talked to, even among condensed matter physicists, didn't understand this connection between off-diagonal Berry connection and optical response. It turns out just to come out of mathematics. It turns out also to have a little bit of a physics explanation. So when you drive a system with light, you're sort of moving the particles around in quasi-momentum, and you're asking how much does that constant change in my state with quasi-momentum eventually couple up to some higher level state. That's kind of the hand-wavy way of understanding this connection. Now I can enter the topic of quantum simulation and say, let's say I want to explore this connection, but even more, let's say I want to measure this geometric quantity, the off-diagonal Berry connection, kind of a weird abstract quantity. How do I do it? Well, I could do it by driving optical transitions on a solid, or in an atoms in optical lattice context, I have a different choice. The equivalent of optical spectroscopy is now looking at the response of the atoms to shaking the entire lattice. The equivalent to optical polarization is the direction in which we shake our lattice. And we can measure the excitation strength at every quasi-momentum, which is something that's hard to do in solids. And in so, we can map out the interband Berry connection directly and experimentally. Okay, so we're doing this in particular now, not with bosons, but with fermions in the lattice, just because we now have a degenerate gas of fermions that we can put into the honeycomb lattice. And what we do is, after loading them into the lattice, we shake the lattice, drive it along some direction, whatever. And then we look at the response. And we've been driving at different frequencies. So we have atoms that fill the lower band of this honeycomb lattice. And depending on what frequency we drive, we can look at transitions either to the second, third, or fourth band of the honeycomb lattice. I'll tell you mostly about the drive to the third and fourth band of the honeycomb lattice. And to look at response, what we do is we compare the momentum distribution of atoms, let's say released from the lattice, with and without this lattice modulation. And by looking at the difference between them, we can see that there's excitations, maybe by the fact that atoms are depleted out of the first Brillouin zone, for example. We can see that there's excitations at specific quasi-momenta and not at other quasi-momenta for every frequency at which we drive our lattice. Here's data that kind of illustrate that. So here's driving atoms at a range of frequencies that would drive them from the first to the fourth band, it turns out. And we see if we drive at low frequencies, there's a little response by atoms right near the M point of the Brillouin zone. And then as we keep increasing the frequency, that response strengthens. So somewhere around here, there's a resonant response. And if I can measure the rate of excitation at that resonant point, then I basically can measure the square of the off-diagonal Berry connection, one of the components of that Berry connection. And as we keep increasing the drive, you see that the resonant position moves from here eventually all the way to the K point. But you also see that the response at the K point is smaller than it is at the M point. And that's telling us something about the magnitude of the off-diagonal Berry connection at that location. Okay, so we take these kinds of data, we figure out what is the resonant frequency and then the strength of the response at every resonant frequency. And from that, we get a projection squared of the interband Berry connection. So here's the data. What we obtain by shaking the lattice in X and Y, we're looking at a two-dimensional lattice, and at angles and in circles, whatever, we shake in all sorts of polarizations. We can determine the magnitude of the X and Y components of the off-diagonal Berry connection. We can also figure out the ratio of these two, AY over AX. Other information, like the actual sign of AX and of AY, we can't obtain by our method. And in fact, we should not be able to obtain by our method because those are gauge dependent. So here's experimental data, let's say on the drive from the first to the third band or the first to the fourth band. And you see the experimental data match the theoretical data remarkably well. That's pretty cool. Even subtle features of the band structure where there's nodes in the interband Berry connection, we reproduce in our data quite nicely. I also plot to you the argument of this ratio. In theory, the ratio between the X and Y components of the interband Berry connection is a complex number. Like, the off-diagonal matrix element for position can be complex. That's true here as well. For the reasons of symmetry of the honeycomb lattice, which is kind of a subtle statement, it turns out that ratio should always be real. And in fact, our data confirm that the ratio is always real. The phase between of this ratio is always either 0 or pi. That's what's given by these two numbers. Okay, so that's the magnitude of components of the interband Berry connection. But what about the actual vector field, the interband Berry connection? The interband Berry connection is a vector that is in real space. It has dimensions of position. And it's a field because it has a value that varies all across the Brillouin zone. So can I get that entire vector field from my work? And to do that, we have to fix a gauge. So we measure the ratio of AY to AX, and we find that it's always real. Now, given that, I can associate this ratio with the tangent of some direction. That's the direction in which the interband Berry connection points. And this quantity beta, this azimuthal angle, has a different value at every position in the Brillouin zone. But the ratio AY to AX does not uniquely determine the value of beta, right? Because the range of the arctan function is only a range of pi, not 2 pi. So now I have to fix a gauge. I tell you in every region of quasi-momentum, when I take the arctangent, on which region of pi should I evaluate it? And we choose for this gauge fixing a value eta, about which is at the center of this range. Now, and in doing so, we pick a gauge in which to represent the vector, the interband Berry connection. And I'll show you some different gauge choices that we've made in analyzing our data. One is a continuous choice of gauge, where this value, this range to which we project the arctan function is continuous in quasi-momentum. And another choice, which seems perverse, but I'll show you that it has a purpose, where we actually have a discontinuous gauge definition, where the range suddenly changes from one range to another across some location in quasi-momentum. Okay, now having done so, let me go ahead and show you what is the value of beta as a function of position, experimentally determined for the interband Berry connection. So particularly, we're looking at the interband Berry connection between bands 1 and 3 of the lattice. And I'm going to look actually first at this discontinuous gauge choice. So here in color, I'm showing you this azimuthal angle beta, which shows me the direction of the vector A in the XY plane. It has values, that's kind of pretty. But now let me look at these values at some interesting points. Let's follow a trajectory in a circle around either the gamma point, the M point, or the K and K prime points. So as I follow a loop around the gamma point that's shown up here, I find that the orientation of beta continuously evolves and it winds around twice. Okay, that's interesting, but everything's continuous. As I circle the M point, I see again that beta varies continuously. I mean, there's a 2 pi jump, but that's just in the definition of beta. Yeah, because I'm not going to get to the second. But there's nothing, it just winds around once. Nothing really dramatic happens there. But at the K and K prime points, things are different. You see that beta continues, but always has a jump of pi. It has a jump of pi, actually specifically at this location where we've made the gauge choice discontinuous. That was actually on purpose. And this pi indicates the presence of a Dirac string that connects the K prime point to the K point. Every K prime point is connected to every K point by a Dirac string. And this Dirac string is something that is inherent to this particular vector field. It's movable. So for example, I can use a different gauge choice that's shown here in this continuous gauge choice. In this case, if I follow a loop around the K or K prime point, I see that I have 3 jumps of pi, but 2 of them I can eliminate by a gauge transformation, which is actually what I've done over here. But the third one I can't get rid of. So there's like an irreducible Dirac string that we can visualize directly in our data for this particular interband Berry connection. It's not always there. If I look at the interband Berry connection between bands 1 and 4, here's, for example, a continuous gauge choice. There are no glitches. There are no Dirac strings. I can perversely add strings by making a discontinuous choice of gauge, but you see that now the strings come in pairs. Here's a jump of pi, and then here's another jump of pi, so they cancel each other out. Okay, so we can directly visualize the Dirac strings in this geometric quantity, the interband Berry connection. Where we're going, we're interested eventually in putting atoms in flat bands of lattices where it turns out this non-dispersing band comes about because of geometric frustration. This can be done either for the honeycomb lattice, which we've been working with, or also the Kagome lattice, which we've studied in other work. And now that we have access to quantum degenerate Fermi gases, we're quite excited to study systems where the Fermi gas enters a flat band, and we have to study the physics of what happens as a result. We can talk about that separately. But I have 3 minutes, and that allows me to talk very briefly about another direction in my group, which is learning how to laser cool a new set of atoms. And you may argue that given how many quantum degenerate gases we have on hand, we don't really need any more. I mean, we've got bosons, we've got fermions, what else do we need? But it turns out that there's some applications in quantum simulation where maybe we don't feel we have just the right atom yet. And one of the ones that really sticks out to me is the effort to try to make topological superconductors. I'm going to have to blitz through this without explaining anything, but there's realizations that people are proposing both in condensed matter and in atomic physics, where p-wave pairing in a superconductor gives the superconductor a certain topological nature. That shows up in the nature of boundaries on this topological superconductor. And it turns out that we don't really have the right atom per se to study this problem. We need fermions with tunable interactions. So we have a handful of those that we can study thus far. But we want ones where you can both drive spin orbit coupling with light and where you don't have very strong magnetism, which kind of gets in the way of spin mixtures. So that kind of led us to explore the periodic table a little bit more. We came up with the idea that actually very many transition metals can all at least be laser cooled on the way to producing quantum degenerate gases. And among them are quite a few fermions. And if we can start laser cooling these atoms and adding more fermions to the ultra cold family, maybe we'll really open up some new work. We've been focusing on atomic titanium, and we've learned how to laser cool by now all 5 isotopes of atomic titanium. Titanium has a very complex energy structure because it has 4 electrons, 4 valence electrons. But within this complex structure, it turns out that there's a long-lived metastable state, which turns out to be highly magnetic. But anyhow, a long-lived metastable state where there's actually 2 laser cooling transitions, we believe. Well, now we know. One of them, which is a broad laser cooling transition, like the D2 transition in an alkali metal. And another one is a narrow line, which was estimated to have a line width of 11 kilohertz. We've now measured it, has a line width of 18 kilohertz. But anyhow, it's pretty narrow. And these should allow for laser cooling. So we built up an experiment that was just meant to see whether laser cooling was possible. To summarize it briefly in words, we use a titanium sublimation pump to produce a sublimated gas of titanium. We pass these titanium atoms through light that pumps them into the metastable state, and then we run them directly into a magneto-optical trap and hope to catch the low velocity tail of what's coming off the IISER pump. And this works. The first success was laser cooling all of the, okay, I'll run just a couple of minutes over, I apologize. All of the zero nuclear spin isotopes of titanium. Those are bosons. They're interesting, they're great. They're all quite abundant. They're easy to laser cool because there's no hyperfine structure. There's also these two fermionic isotopes of titanium, titanium 47 and 49. They have a non-zero nuclear spin. That means that they have hyperfine structure, and the hyperfine structure actually had not been measured. So we had to first of all measure it. So that was really fun. And then now knowing the hyperfine structure of the relevant lines, in particular, the line that we use for laser cooling, we know that we can add not just laser cooling light, but also a couple of repump tones. And on applying those tones, we also make magneto-optical traps of the fermionic species. So we have them on hand as well. The most recent development is that we've also now learned how to laser cool on the narrow line transition, this line that's at 1040 nanometer wavelength. And again, lack of time, I won't be able to tell you, like, this is a very strange magneto-optical trap because narrow line magneto-optical traps are just kind of weird in how they behave. I learned a lot along the way. But in the end, we have now produced a narrow line MOT where in 3 dimensions, the atoms are cooled below a microkelvin just directly with laser cooling. So titanium is looking like a very handy atom for future quantum simulation research, whether it's the study of these topological superfluids or it's other things too. We have ideas for how to put titanium atoms in optical tweezers and kind of follow that whole line. We have ideas for building an optical atomic clock with titanium that has a wavelength that is right within the telecom band of wavelengths, and that would be useful as well. But then I'm out of time, so let me just wrap up. So I've told you about results that have come out of my team of people working with atoms and optical lattices, and the team of people working with ultra-cold titanium. I mentioned theory collaboration we have with people at the University of Delaware, particularly on the titanium project. And the work coming out of my atoms in optical cavities experiment, you'll have to hear about next Monday. With that, I'll finish. Thanks a lot.
Thank you very much for this nice and insightful presentation. We have time for a few questions.
So this is regarding your first part of the talk where you're working with a mixture of rubidium and potassium.
Yeah.
So potassium is gifted with very broad flashback resonances, so you can change the interaction. So did you keep the interaction fixed, or what role the interaction had in this measurements?
Yeah, thanks. So at this point, we've been laser cooling mixtures, or sorry, reducing through evaporative cooling quantum degenerate gases, both of rubidium and of potassium. The potassium quantum degenerate gas, we're working with potassium 40, the fermionic species. So far, we've only been working with a single spin component. The Feshbach resonances, as you know, will come about when 2 different spin states interact with one another. So actually, with the atoms all in the lowest spin state, there's no interactions, right? And that, I think, that's not ultimately very, very interesting physics-wise, but it was handy for doing some very quantitative assays of band structure where interactions weren't confusing us. We will turn to the Feshbach resonances soon, and that's where the interesting physics, in particular of these non-dispersing of these flat bands, has become really evident.
Thanks for the nice talk. So I was interested about the titanium.
Yeah.
So 2 questions. One is, what is the phase transition temperature for bosonic species TC and even TF, means roughly for your parameters? This is one. And probably I missed the argument about the titanium with low L. What is the special advantage over other species?
Yeah. So let me first talk about the advantages, and then I'll talk about the setting. Right. So there's two notable things that I see about, well, there's many. There's a few notable things that I see about the transition metal. One of them is that they have a state that has a non-zero angular momentum, electronic angular momentum in the ground state. What that means is, let's say in the ground state, titanium has a anisotropic electron distribution in its core. And for that reason, maybe for that reason, it's easy to understand that if you now drive this atom with light of different polarizations, it'll respond very differently to different polarizations. That's to say that the optical polarizability of a ground state titanium atom is very anisotropic with polarization everywhere in the spectrum. So for the alkali metals or the alkali earth metals, when we want anisotropic optical response, for example, maybe we want to drive Raman transitions, we always have to work very close to an atomic resonance because otherwise the atom itself is just a round ball of electrons. It doesn't know anything about the direction of polarization of light. But for titanium, it's different. Everywhere across the optical spectrum, you can drive Raman transitions, you can have state-dependent optical forces and all that. And I think that's going to be quite a big resource. Different from the lanthanide metals, at least in its ground state, titanium is not very magnetic. It has a magnetic moment of 4/3 of a Bohr magneton. So I think spin mixtures in titanium should be very long-lived, like they are in the alkali metals. And that means that I can get both, let's say, the anisotropic optical stuff, which gives you spin-orbit coupling, but also have spin mixtures that can interact with each other. And that, I think, is this pathway. So like for the topological superfluid, I need fermions, I need strong interactions, I think we'll have Feshbach resonances, and I need spin-orbit coupling, and I need spins that interact with one another. So I think we can get all of those in titanium. Next, you asked about TC. Yeah, I mean, we've just laser cooled the thing. I don't see any reason why we shouldn't be working with gases at the same density as we do in other experiments. So you can just look up what is the TC and TF for potassium, which is 2 lines over, and that'll be the same as for titanium. So, you know, microkelvin, half a microkelvin, those will be the relevant. The fact that we've already laser cooled to below a microkelvin isn't really amazing because we're still working with a very low density gas. So time will tell whether we can really push all the way to quantum mechanics.
There are more questions in the audience, but I think in the interest of time, we have to move on. And Dan has assured that he's available 24/7 for the next week at least.
I will
Thank
be.
you very
With
much
jet lag, it is
for the
true. Yeah.
interesting presentation.